I'm talking today about machine learning in Julia. And so we have what is called binder. So if you click on the link that I put in the chat, there is a GitHub repository and there's a launch binder, so you can sort of use the tool without installing Julia and play with it and follow our tutorial. We also have a Journal of Open Source Software preprint, which is sort of a which sort of talks a bit of the design principles and why we did things the way we did them. So coming from originally from quite theoretical background and then moved to a bit more applied background, so I noticed that there's sort of bottleneck that you often you do a proof of concept in R and you do it quick and dirty, and that's sort of sufficient for writing a paper or getting first results. And then you there are engineers that help to productionize it, to make it faster, implement certain aspects in RCPP, and then you change something and then they have to change it. And so you have sort of this two-language problem, because it's never that the prototype is nice and clean and just needed to be translated. There's always sort of this unfortunate loop where there's a mismatch and it's a lot of backwards and forwards. And so for the last 2 and a bit years, I've been working with the Julia programming language, where the premise is that you write something that looks like R or Python, but it's as fast as C, and it's also sort of has the ability for code to be reused both on CPU, GPU, and other settings. And so this makes writing software much easier. And so there's a first sort of reason of why Julia, and I don't want to go into too much detail about it. It's very easy to learn. It has a good type system, and it has a good ecosystem interoperability, which means you can call Python and R very easily. So if there's certain aspects, you can sort of flip and just take out the Python and put a bit of Julia in there, because you can both call Python from Julia and Julia from Python. And so there have been quite some substantial case studies. So in the US, for instance, the Federal Aviation Administration uses it to prevent collision in the air. The risk platform from BlackRock is built on it, and so there's an increasing amount of pickup of this language from industry, as well as sort of research organizations such as NASA. And the ecosystem is sort of originally comes from a quite sort of numerical analysis viewpoint. There's a lot of work on sort of ODEs, PDEs, stochastic differential equations. If anybody's simulating stochastic differential equation, I would highly recommend to check out differential equations.jl, which sort of is, to my mind, has the biggest set of different numerical integrators and way to plug and play with it. And so in the last couple of years, there has been from the differential equations, there has been to what is called scientific machine learning, which is sort of the idea of combining mechanical equations such as SD and ODEs, and having within them components of machine learning. So say there's an aspect of an ODE that you don't know, so you plug in a neural network there. And so this work has been done out of MIT and has a huge uptake in terms of climate, for instance, Climate Modeling Alliance and so forth. And now coming to what we've been doing. So we have been taking a sort of slightly more sort of practical data analysis viewpoint and looked at machine learning in Julia. So just to say what our principles were. So if you sort of want to entertain your kids at home and you want to play with a castle, then Playmobil Castle is great. It's exactly if you want to play with this particular castle, but it's not good if you want something which is slightly different. So if there's something that you doesn't fit in in what the creators have envisioned. And so if you have Lego, you have a lot of user contributed models. You buy 3 models, but in fact you have 10 because you can get the instructions for all the others. And so that's sort of a bit what machine learning in Julia is aiming for. We want to be fast, and we want to give you a very tidy work frame to do the work that's sort of required. And we want to support you building your own snake power train. So that's something my daughter actually built. Well, just combine 2 models. So what is MLJ? MLJ is a toolbox for selecting, evaluating, optimizing, combining over 120 machine learning models and types. And so what we want to achieve is sort of Julia is great for research code already, but what we also want to able to do is for people actually performing data analysis. So the ones that use maybe Carrot or scikit-learn and do data hands-on data analysis. So this is what is commonly called machine learning toolboxes. And so the most popular ones are above: Weka, scikit-learn, Carré, MLR. And so the idea is to codify everything from the pre-processing and the feature extraction, the imputation, the model building, and expose all the hyperparameters that are used in between, and do a rigorous evaluation. So this can be sort of shown by a Wall-E type cartoon, where you have these hyperparameters, the model tuning parameters that affects the model fitting and therefore the prediction and performance on new data. So it's very simple. So if you choose one of the existing models, it's the code is literally a few lines to train and to choose what kind of cross validation, what rows to train on, and to predict on new data. So we've created a multitude of GitHub repositories that go from sort of MLJ models, which contain the models, to MLJ tuning, which has Bayesian optimization for model tuning, and other Latin hypercube, random search, and grid, and others. And so we've made sort of this ecosystem of little packages that all work together, and that ensure that we have collaborators that work and help us to build this. What is really nice is that, say you have your own model, you can make it available for everyone, and you can, if you just want to try out MLJ, you literally need sort of define a structure which contains the parameters of hyperparameters of your model, and then you can make use of like all the facilities that we've created. So be it the one-hot encoder, the ability to transform the labels, and then you have your custom code here of this model, and then you still expose all the parameters that can be used to tune the full pipeline. Yeah, so I think in the interest of time, I will make only very brief remarks on the fairness. What is nice is if you have exposed them all in this sort of common interface, you can support you can support meta algorithms, and some of the fairness algorithms can be seen in this way. So let's consider the Compass dataset. The Compass dataset is used to predict whether a criminal will reoffend after being put on parole or being released from jail. And so this score in the US is given the parole board and help them to make a decision if they should release this person or not. And so there's been a big outcry that this system was unfair. And so what is important to sort of say is like what we mean by unfair. There's a lot of sort of strong personal and ethical considerations what fair means for an individual. But the point is that there have been very many definitions of metrics that characterize certain aspects of fairness. And so what is relevant for the particular problem at hand is dependent. There are some nice papers that make suggestions depending of if intervention is punitive or assistive, of how large the intervention is, and so forth. And it's from a domain area, it makes a lot of sense to look at the false negative rates. So this looks at basically the fractions that are labeled that are predicted negative but are labeled positive. So the way that sort of in this case are labeled in this case that should be able to be released but are labeled not to be released. Yeah, so they're called negative, but they should have been labeled positive. And so this false negative rate looks at this ratio of the false negatives divided by the labeled positives. And this disparity is taking one ratio further so you do this group specifically. So A is a group, so say this could be the race, so Black, Hispanic, white. And the disparity is defined by taking a reference group, say white, and looking at the ratio between the metric for an individual subgroup. And so what you can do, then there are certain models that reweighing, for instance, the instances, or that use linear program to find flipping probabilities. So when should you flip the label for a certain group with a certain probability to improve the fairness? And so this sort of wrap models allow you to take any base model and combine them with these meta models. And so having this sort of very composable structure pays off in this case. So we submitted a paper to the Fairness, Accountability, and Transparency Conference, and what we've studied there are aspects of generalizability. So I think in the interest of time, I just sort of summarize this in a few words. So you have different sense of this imbalance. You have imbalance of the labels, of the Y labels, and you have imbalance of the class labels A. And so this causes a high variance in the estimator of a generalization error. So what we have done is sort of looked at how can we estimate the generalization of error of the fairness. You don't care necessarily about improving the fairness on your training data set. What you want to be sure of is you actually improve the fairness on the unseen data set. And that's what we sort of studied. Thank you for your attention.